Good morning, everybody. I hope everyone's having a wonderful day. Let me take all this off. There we go. Whew. It's spooky time. It's spooky time. I had to do this a little early because we don't have class on Sunday. So, there we go. Here we go. Yes, it's spooky skeleton time. Exactly. So, anyways, I hope everyone's having a wonderful day. So, today I wanted to get into talking more about it appears I lost my headpiece in there. Let me go get my other earpiece. That's pretty hilarious. Let me get my other earpiece. I want to make sure I can hear everybody. Wonderful. See, that's a botch for you. Anyways, so hope everyone's having a wonderful day. So today I'm going to be talking more about graph traversal algorithms with you. And in particular, I'm going to be moving into, depending on how far along we get, I'll be starting to talk about some problems we can solve on graphs that are of a very specific kind. So before we start, are there any questions other than how I look at the moment? Because it's, like I said, it's spooky skeleton time. And yes, I made sure I'm wearing my glasses so I can read the chat properly now. Oh, wonderful. Okay, so if there aren't any questions, let me proceed. So anyways, last day I had introduced you to breadth first search. So remember, breadth first search, the whole idea is, remember, I had my exploring cap on and I was in the jungle looking for the lost temple of awesome. And the way I would do it is I would do it breadth-wise or breadth width by simply taking incremental steps and just exploring all that within that incremental step as I go forward and forward and forward. So what that's going to translate into for our breadth first search is the number of edges that I'm going to be using at every single part of my search. As we're going to see, that's going to have a very nice application for breadth first search later on in this lecture. So just as a reminder, remember the key data structure in breadth first search is in fact a queue. So last time when we talked about depth first search, we'd had the stack was our main data structure we had used. Here we're using a queue. So the whole idea works like this. The principle is very similar. Is that whenever I'm going to encounter a vertex in the graph, I'm going to mark it so that I know that I've visited it. So that when I reveal it out of the queue, once it gets its turn, then I know that no other time it's going to get placed in this queue again, because I already visited at least once. So when I have vertices in my queue, every single time I'm going to perform a dequeue operation to get the next node or vertex out of my queue. I'm going to do stuff to it. For our purposes in our analysis, I'm just going to assume this process is just something like, oh, I'm going to check something about that vertex, or I'm going to mark something, or I'm going to do something here. It's probably going to take some. I'm going to assume this takes constant time, and then I have to check all my incident edges, just like what I did with depth first search. And then this is actually pretty much almost exactly the same. The only difference now is you're going to notice that instead of having it where if I encounter already a marked vertex, I'm going to call it a cross edge as opposed to a back edge. There's going to be a reason why I'm going to call it this. Otherwise, I'm going to label the edge as a discovery edge. And then we're going to enqueue in the other endpoint, the one I've just found. But I'm going to make sure I mark it before I proceed to another iteration of this process. So that's generally the idea with depth for breadth first search. It once you understand depth first search, breadth first search is just simply going to be where we take the same idea, instead of having it a stack, we're going to have a queue, and there's just some small little wrinkles with the way we have to carry this out. So are there any questions about breadth first search itself? Just the way I've laid it out here. So I wrote this last day, but I just want to make sure everybody's on the same boat with this before we proceed. On the spooky boat. Okay, so I think we're gonna give me 2 thumbs up if we're doing all good. Okay, great. I literally see a whole bunch of thumbs up. That's wonderful, wonderful. So anyways, if that's the case, I want to just bring up one thing. Yes, we're going to be walking through a full example here in a moment. But I want to elaborate on one detail that's very important for breadth first search, and it's actually quite closely connected to what we were doing. Well, this is the code. This is the algorithm. So what I'm doing here is I want to take a parallel between depth first search and breadth first search. In depth first search, we had a depth first search tree, a DFS tree, right? Well, there also exists another thing just like this called a breadth first search tree. And like that one, it also has properties. So I'm going to actually make a small modification to my pseudocode over there. So for my algorithm, I'm going to make a couple modifications to keep track of the information for this BFS tree, the so-called BFS tree. And you can do something quite similar to this for DFS if you want to actually get the tree. So what I'm going to do is I'm going to assume each one of the vertices has an attribute called its parent. So since I start at vertex U in this process, that means that it's not going to have any parent with respect to this tree, because that's going to be the root of our tree. Then what's going to happen is every time I'm going to consider another opposing endpoint and I place it into the queue, I know its parent at that time when I place it into the queue. It's in fact right when I mark that vertex. So if I want to know what the parent of W is, that's the opposing endpoint for the vertex that I've pulled out of the queue. Its parent is going to be V, because remember, that's the opposing endpoint for W. So I want to keep these 2 things in mind when I'm doing this example so I can illustrate how you can build the tree. And you can do the very similar thing with DFS if you want to know how to build this tree. So for each one of my vertices, so I have a graph right here. I'm going to assume each one has a parent attribute, just like I've laid out over there. So all these are going to have a parent, another parent, then another parent, and another parent. So I need to make sure all these have parents. And I'm going to assume at the beginning of this process that all of these, they may as well just be null. I'll just call them, I'll say right nil. I'll just assume that there's no parent quite yet. And I think I got them all. Okay. So let's walk through BFS. Let's see how this will work if I make the starting vertex, in this case, what I've written there is U, if I make that vertex 1. So when I start off with vertex 1, what I do is I enqueue U into the queue. So that means I'm going to place vertex 1 into the queue. Then I'm going to mark it. And then what I need to do is I'm now going to enter into that loop, because notice that the parent is still null, right? So keep in mind, like I said, I'm just doing this out of convenience for us. I'm going to update this as we go. So now I'm going to go through our queue. I'm going to now try to empty out the queue. So every time I do this, you're going to notice that there's going to be a very specific way it's going to happen. But the queue makes this process very easy to accomplish. So first I'm going to dequeue out V. So that means that I'm better. So I'm going to dequeue 1. So now 1 is out here. And now I'm going to consider all incident edges that are not labeled for that vertex. So now what I'm going to do is I'm going to go through and I'll just say, okay, well, looky here. Okay, looky, I found one right here. And let me just use a other marker. So I'm going to label that as a discovery edge. And then I'm going to enqueue in 2. And then I'm supposed to also mark it. And then I'm supposed to update its parent. And its parent was V, so the parent now is 1. This parent is 1. And then, let's see here. So now we've gotten that part down. Now we need to do another iteration of checking over all the incident edges of 1. We're not quite done with 1 yet. So now notice I have another incident edge right here. Notice its other endpoint is not marked. So what I'm going to do now is I'm going to label this edge as a discovery edge. I'm going to label those in red. And then I'm going to NQ in vertex 8. I'm going to mark 8, so I know I've already been here. And then I'm going to, of course, update its parent to be 1, just like I had with 2. So now notice that when I did this, every single time I now look at, I've considered all of the incident edges on 1. So that means that now, as far as I'm concerned, now I'm done with 1, right? I've looked at all of the incident edges on V in this case. And now that means that I'm going to now have to do another iteration of the outermost loop. So now I look at my queue and I say, hey, look, what do I need to DQ next? Well, it's this 2 here. So now we take the 2 out of here. And now we're going to play around with this 2. So now I walk through all of my incident edges for any one that isn't labeled yet. So let's start off over here. So I've encountered this right here. And then I say, hey, look, well, W isn't marked, right? So that means that I better do something with this. This is indeed going to be a discovery edge, as I've indicated here. I'm going to mark it, and I'm going to place it into this queue. So 3 goes into the queue. And I need to update its parent. Its parent is now 2. Its parent is 2. And now let's see here. I think I'm done with that part. Now let's proceed. Let's say now I consider the next incident edge. Remember, the order in which I do these doesn't matter. I'm only considering all the incident edges on 2. That's all that's happening. So next I'm just going to I'm going to consider this incident edge. Notice that this endpoint here is the W is in fact not marked. So I found another discovery edge. I'm going to label that. I'm now going to place 4 in my queue. I'm going to mark it, and I'm going to update its parent to be 2. And then, of course, what do I need to do? Well, I think it's everything I have to do with 4 at the moment. Now let's consider this incident edge. What's different about this incident edge? Can somebody tell me? What's different about this one? Yeah, exactly. Both endpoints are marked, exactly. In particular, this W is marked. So this is when we're going to label a cross edge. And now, when I have a cross edge, I'm not going to proceed to put 8 back into this queue again. I already have 8 in that queue. So, then one neat property about this is that either 8 will already be in the queue or it already has to have been considered in the queue already. So that's why we label this as a cross edge. So now I think we're done with 2, right? I think we're done with 2. So now next, let's DQ again. So now I have to look at 8. So now let's take a look at all the incident edges here. Well, let's take a peek. So suppose I consider this incident edge. Well, we have the same issue over here, right? This is in fact a cross edge. So we know that we're definitely not going to put 4 into this queue. 4 actually is right there in the queue. Yes? Yeah, exactly. So when I was looking at, yes, exactly. So you notice that I could have set, because remember, this loop just goes through all of the incident edges on V, and in this case, V is 8. So you will technically have it where you're going to go through each one of the incident edges, and you just check if it's labeled or not. So indeed, you're right that you would have it where you would have one iteration of this loop where it will just say, okay, well, VW, which would be 8.2, that is already labeled. So that means I shouldn't do anything with it. Exactly, exactly. Wonderful question. So you'll notice that I'm going to start just skipping over those edges because they just don't do anything interesting for us. So those will just be iterations where I'm just going to check that and say, oh, that if statement failed. So I'm not going to do anything inside here. Wonderful, wonderful. So now let's see here. So we got the cross edge there. Okay, so now here, however, notice that I have this opposing endpoint. That one definitely is not marked. So that means I've definitely found an edge I can definitely go a little further on. So that means that I better do what? I labeled that a discovery edge. I need to NQ in 7. And then I mark 7. And then now I'm going to label its parent to be 8. To be 8. And actually, just let me make that mark a little bit easier to see. There we go. For dramatic purposes, let's make this X really big. So let's see. So now I've considered all the incident edges on 8. So I think we're done with 8. So let's proceed to the next vertex that's in the queue. I'm going to DQ out 3. Now we're going to look at 3. I've already labeled this edge, so I don't really have to worry about it. And then what I do is I look at this edge here. Notice that this edge, for example, its opposing endpoint here, is in fact not marked. So I'm indeed going to need to label this edge as a discovery edge. I'm going to then enter 5 into my queue. I'm going to mark this, and then I'm going to just quite simply assign its parent to be 3. And now look at this. 3, I've considered all the incident edges on 3. So we're done with 3. So you're going to notice as we go along, this is going to get a little faster and faster because the number of edges, I'm starting to run out of them. So let's see. So now I'm going to DQ out 4. So now 4 is now out of the queue. Now I'm looking at 4. I look at all my incident edges. So of course, this one's already labeled, so I don't need to worry about it. This one, however, that one is in fact not labeled. But notice that its opposing endpoint, this W, this would be W in the algorithm. This is already marked, so we most certainly will think that's a cross edge. If I, of course, consider this one, that's already labeled, so I don't have to do anything. Then I proceed to this edge. This edge is not labeled, however, that's marked. So most certainly that is going to be a cross edge. And then what's going to happen? What's going to happen? Well, what's going to happen is we're going to have it where this edge, is this a cross edge or a discovery edge? This one right here. Can somebody tell me? It's a discovery edge. Exactly, perfect. So you're all pros at this. That's wonderful. So now we've got our discovery edge. That means I'm juggling around markers. Good thing I'm not actually trying to juggle them. I'm not the greatest when it comes to juggling. Balancing I can do, but juggling I'm not the greatest at. So let's see. So now I need to put in, so I take and put 6 in. I'm sort of running out of space on my queue here. That's just my drawing. That actually has nothing to do with the queue itself. So I'm going to NQ in 6. I'm going to mark it. And I'm going to update its parent to be 4. So I've looked at all the incident edges of 4. So we're done with 4. So let's proceed now. Let's DQ 7. This one's even easier. So let's proceed. So 7, this edge is already labeled. That edge is already labeled. This one, however, is not, but notice its opposing endpoint, the W in our algorithm here. It is in fact a 6 and it's already marked, so I'm going to label this with a cross edge or discovery edge. Cross edge, perfect, wonderful. So now we're done with 7. Now we look at 5. Okay, I DQ 5. The great thing about this one is that all the edges are already labeled, so you'd consider each of these and look and, oh yeah, they're already labeled, so I don't have to do anything for each of those iterations. So 5 we're done with. 6, I'm going to DQ that. Notice, same deal. All of the edges are already labeled that are incident on 6. So So this actually is the full execution of BFS on this graph. Notice that every vertex is indeed marked, and every edge is in fact labeled. And one other fact that I want you to notice is look at the red edges. These are our discovery edges. What is that? Can somebody tell me what that is? It's a tree, exactly. Perfect, it's a tree. So we call the these red edges, so the red edges, or our discovery edges, are the BFS tree. So this is our BFS tree. So this is the breadth first search tree. So this is also a property that you get from BFS, is that you're going to end up, all these discovery edges are going to form a tree. So this tree actually has some special properties I'm going to talk about in a moment. So like this is one of those things I want you to keep in the back of your mind whenever you think of whether you should pick DFS or BFS as a graph traversal algorithm, is if you really need this feature I'm going to talk about in a moment. So first, is everybody okay with this example? Is there anything I need to clarify with you about how I did over here? Are we all good? Just don't be shy. Don't be shy about asking questions. I'm here to help. Let me just make sure I got... Okay, I think we're okay. So now what I want to do is I want to do the analysis of the running time of BFS. Like DFS, I need to consider both my different graph representations. So first I'm going to analyze this without taking that into consideration, quite like I did with DFS. And then I'm going to just walk through each case. Now I have a more delicate write-up in the notes, so take a look at that after class. But I'm going to just walk us through this process. So the first thing is remember about your queues. Now remember, this is a queue. It's something that you can implement a lot of these operations quite efficiently with a link-based approach. So first off, setting up an empty queue. And you can end queue. Both of these operations I can most certainly do in constant time, right? So I can create an empty queue, I can end queue, and I can mark all these I can do in constant time, correct? So I can most certainly do all of these so all of these I can do in constant time, right? Now, next you're going to notice that I now have to consider this loop. So notice that this while loop depends on the queue becoming empty. So the first thing I need to do is remember how many vertices are going to end up in this queue. So for the sake of our analysis, I'm going to assume that the graph is connected. So how many times is that loop going to iterate if the graph is connected? If n is the number of vertices or m is the number of edges? How many times is this while loop going to repeat? So how many times is this going to happen? N times, exactly. So notice that this loop here, so we know that, so just keep it in the back of your mind that this is going to happen n times because I'm going to have to consider all of the vertices here. So let's look inside here. So dequeuing, I could do that in constant time. I'm going to assume process takes constant time, but it doesn't necessarily have to. But for our analysis, I have to assume that, or at least something comparable to this. So I know this stuff all right here. Okay, all of this I can definitely do in constant time. Keep in mind, you can always write constants for these. I'm just doing this for the sake of time. And then now for every one of this, we have to be very careful because inside here, notice that this depends on this incident edge. So this is going through all the incident edges on a given vertex, in this case V. Inside here, all of this, the great thing about all of this is all of this takes constant time, right? Like I can check if the edge isn't labeled in constant time. I can check that the vertex is marked or not marked. I can label an edge. I can also do this NQ, and I can also do these markings as well. All of this I can do. All of this in here, I can do in constant time. But however, there's this part right here that's a little unclear. So you know that this is going to end up being dependent on the number of iterations if this is constant time. So you end up getting it where this whole part here, this whole loop, is going to depend on the number of iterations. Sorry, that's supposed to be an N there. There we go. Number of iterations of this loop. So that being said, actually, well, technically it's some constant times that. But like I said, what I'm going to now have to do is take this into account with this outermost loop. So you know that this is going to depend on two things. It's going to depend on considering all of the vertices in the graph. That's what this loop is going to get us to do. And it's also going to depend on us computing all the incident edges. So, yeah, no worries, that's fine. But anyways, so the big thing here is just keeping in mind that we have to consider all the vertices, and I have this issue with those incident edges. So I'm going to address both of these right now. So you know that this just to make it clear, this goes through all vertices if G is connected. So just keep that in mind. So I'm just going to address these two parts that I have not really talked about yet. So let's move on over here. So let's move on over here. Now I'm going to look at it from both of our representations. So the first one is going to be our adjacency matrix, then the other one is going to be our adjacency list. And the great thing about this is this should remind you so much of when we did our analysis for depth first search, so I'm going to be kind of brief about this. Like I said, if you really want to get into more detail about this, just take a look in the notes. I go into a little more detail there. Sorry, the camera is just a little spooked by me. Spooky, spooky skeletons. So first for the adjacency matrix, remember that loop inside where I check all the incident edges? Remember, I have to go through all the incident edges, so it's going to depend on how I represent the graph. If I'm looking at all the incident edges in an adjacency matrix, that means I'm going to have to check an entire row. In the worst case, that simply means it's going to take big O of n time, where n is the number of vertices. And since n vertices are DQ'd, that means that overall, you're going to end up having it where that loop over there depends on the number of iterations, which is n. Then the outermost loop is going to consider all the vertices. So that means it's going to run in big O of n squared time, which isn't bad at all. It's not bad at all. The adjacency list, however, it's the same idea here. We have to compute all the incident edges. That means we're going to have to look at a given list. And that means I'm going to have to consider degree of V nodes in that linked list of the adjacency list. But by the handshaking lemma, remember we talked about this last day, that means that I'm just going to have big O of m operations that are going to happen over all of the vertices, because I'm going to have to consider each vertex. And each vertex will have its degree of vertices, so I do this over all of the vertices. That means overall I'm going to have big O of m, but that means that when I put all of this together, now I have to be a bit careful about this, because I go through all of the vertices. So I'm going to walk back over this way, just because I really don't want to lose you on this step, because this is something that creeps up every once in a while. Because when you look at the loop, the way this loop looks, so I really want you to pay close attention to what I'm going to mention here, because otherwise you're going to find that the way I'm going to be counting this seem a little strange. Because normally we're used to seeing, okay, there's a while loop, there's a for loop, so they're nested, so I multiply. That's what normally people do when they do the analysis here. But really what I'm doing is I'm trying to count the operations. So when I did this part right here, I'm considering all of the incident edges on a given vertex. But this while loop considers each vertex at the end of this whole day if G is connected, right? So I have to look at it from the perspective of I have to look at each vertex, which indeed will take me big O of n time to get each one of these vertices, because I'm going to have to perform these DQ operations and process it in constant time in some capacity. I'm going to have to do that for each one of the vertices. But notice that for each vertex, I consider something that's involving the degree of that vertex for each one of its vertices. And if I have n of those, remember, that means I have to consider each vertex. Each one of those, when I sum all those degrees, that's big O of m. So when I count these two things together, I end up with big O of n plus m. Where this part right here, before the loop, this is my big O of n when I'm counting this, because this is going to happen n times, this while loop. But notice for each one of these, I'm not considering every aspect of the graph. I'm only considering incident edges on a given vertex, right? So when I do this for each one of the vertices, I'm actually just looking at each vertex and its sum of its degrees, which that is big O of m. So when you put all these pieces together, you end up with big O of m plus n. So just be wary that I'm still counting the operations. I'm just doing it very carefully here. Hopefully I didn't lose anybody on that explanation, but you just got to remember, I'm just trying to count. Can you review the handshaking lemma? Remember, the handshaking lemma is the following. Remember, the handshaking lemma is that the sum of the degrees, so if I consider all the vertices in the graph. So this is saying for each vertex in the set of vertices, the degree of that vertex, when I sum over all of them, is going to be equal to exactly twice the number of edges. So it's going to be equal to exactly twice the number of edges. But that means that it's big O of m, right? Because that's just a constant sitting in front of m. So that's where the big O of m comes from. Hopefully that clarifies that. So this is why the running time for an adjacency list is big O of m plus n, where m is the number of edges and the n is the number of vertices. That's a wonderful question. That should actually, it nicely completes the analysis I have here. But yeah. Just keep in mind the way I'm counting the operations. It's, like I said, a common pitfall, or I wouldn't call it a trap, it's a pitfall. It happens to the best of us. Is accounting for this as a nested loop and then multiplying the quantities inside, which it isn't that. It's actually that I'm considering each vertex, and I'm doing that over the degree of each vertex, which I can add up all of those operations separately. So I kind of taken this part of it, I've counted all of that, then I'm taking this part and I'm counting all of those, how many times they happen. Okay, so that's all I have to say about really the time complexity. Like I said, all of those you can replace with big thetas if you really just want to be nitpicky with me, but that's cool. Being nitpicky is awesome sometimes. At least in this case, it's fine. You can easily put big theta there and there's nothing that's any issue. But you'll notice that it matches the same time complexities that we had for DFS. Just that's the big thing I want you to note about this. So I want to talk a bit about the structure of the BFS tree actually next. So I said earlier I was going to talk about this. So the first thing is, I never told you last day what the back edges in DFS represented. So if you remember back, just picture it in your mind from last day. From DFS, when I drew you out a DFS tree and it had our back edges. What happened? When did we label a back edge? That happened when I had it where I already encountered a vertex that's already marked as the opposing endpoint, just like what I did here with the cross edges, right? But in a DFS tree, because we go depth-wise in, that means if you actually look at the DFS tree and you ask yourself, what exactly is the opposing endpoint? So if I have my marked one I've already seen, and then I look at mine that I've just encountered, and I label that back edge, what you can say is that vertex that you're just encountering is actually going to have it where that vertex that you're going to encounter as the back edge, across that back edge, is an ancestor of this vertex. So that's one property that's actually nice about the DFS tree, is that you can guarantee that that is always, if you encounter a back edge at where you're looking at, you can guarantee whatever is on the other side of that edge is an ancestor in the tree. So that's one thing I want to point out. Another thing I want to point out is for BFS. So now let's talk about BFS. These cross edges. Now, it really relates to what I'm going to say in a moment, but I want you to observe, and you can see in this example, but it is true generally, is if I look at, say, this cross edge here. Notice I want you to look at how many edges I used to get from here to 2, and here to 8. How many edges did I use? I used one edge, right? So notice that cross edges, like if I were to do this again, okay, how many edges did it take me to get from 1 to 3? I took 2 edges, right? It takes 2 edges to get there. Just like if I wanted to go, say, from here to 7, it takes 2 edges to get there. But notice that if I look at any cross edge, if I look at it like this, now this is the part that really kind of, when you see the picture, I know when I first seen this, it really excited me, is that if you take a look at your picture here, what I've just circled here, these are all of the vertices that I could reach using at most 0 edges. These 2 vertices, these are the vertices that I used 1 edge to get to. How about the ones for 2? Let's see. We've got 1, 2, 1, 2. These are all the vertices that I used, like that I reached once I used how many edges? Let's see, 2 edges. And then lastly, we have these 2 here. How many edges did I use to get to these? So I used 1, 2, 3, right? Let's see, 1, 2, 3, let's see, yeah, 1, 2, 3. Spooky skeletons don't have me counting today, okay? My apologies. So now this is the thing I really want you to observe, is that when you look at the number of edges I use to get to a vertex, you can look right at this BFS tree if you're just not sure what I mean. You just look at the number of edges it takes me to get from the start vertex, in this case the U, which is the root of the tree, to any one vertex. You can look at the number of edges that I use to get there. And this is very much exactly like when I was in the jungle looking for the lost Temple of Awesome. So that's me at the start. This is me after I've explored 1 step into this jungle. This is me when I've taken 2 steps into the jungle. And this is me when I've taken 3 steps into the jungle. This is why we call it breadth first search. Each of these forms a level of the BFS tree. But look at the cross edges. The cross edges, whenever I have a cross edge from, say, 2 vertices on the same level of this tree, cross edges will appear there, or they will appear with the next level in the tree. So that's the property I want you to know about with this BFS tree with the cross edges. This is what makes it different from a back edge, is that these cross edges go from one level to the next, or they stay in the same level of this tree. So that's really one thing I want you to observe about cross edges. Another thing I want you to observe is because of the fact that these form levels in this tree, and they're based on the number of edges in the tree, you can actually do something with that. And this is one of those features of BFS I wanted to point out. So let me just tell you a little bit about this, because this is actually one of those things that if you were asked me like, oh, Dan, I need to do this, and you came and bugged me about this, I'll tell you, oh, yeah, this is maybe what you'd consider if you wanted to do BFS instead of DFS. Because each one sort of has their own pros and cons, depending on what you're looking for and what you want to do. Sometimes DFS is really simple to implement. You'll notice that when I do this queue actually can sometimes get quite big if there's a lot of edges that I can reach at a given level. So another thing that I want you to be aware of is that you can compute shortest ST paths using BFS. So what do I mean by that? Is that if I consider my graph here, like I said, when I go from one level of the tree to another level of the tree, how many edges do I use? I use one edge every single time I go from one level to the next level. So you can actually compute quite easily how many edges I use to get from here to there at any one of these, in between any of these two levels. But notice, because I'm always taking that little, I'm incrementally moving my way to, say, for example, for me, going to the Lost Temple of Awesome. Notice that when I encounter a vertex, I use the least number of edges that get me there. So when I do this, so why am I saying this? So this is, of course, going to be a, so just let me define what I mean by this. So this is a path that consists of a least number of edges. From S to T. So if you pick S and T, just like, remember when I did last day, I talked about pathfinding, right? So this is the S and T I'm referring to, is you would have designated an S and a T. So for example, you would have something like S and T like this. What you can do quite easily is you can just take BFS like I did here. You have the BFS tree, and it tells you your parent every single time. Do you see how you can actually get the path? Does anybody have any ideas of how I can get this path from S to T, or T to S, however you want to look at it? So what information do I have here from this BFS tree that I can use? Yes, we would start traversing. Yes, we'll start traversing with BFS. Now, I must stress that technically you don't have to execute the entirety of BFS. I just need to get from S to T. But once, so yeah, so S is in fact going to end up being the root of the tree, but this will be where I start. And I must stress that when you're doing this, as soon as you hit T, you don't have to explore any more of this graph. That's the neat fact about this, is because it's always going to use the least number of edges. So when I encounter T, I'm going to use the least number of edges. But what information can I use if I get to T and I want to know what the path is? Can somebody tell me? Don't be shy. I'm happy to hear any ideas that anybody has about this. Yeah, check the parents. Exactly, that's exactly it. So look at this. So I could just, so notice that once I compute this part of the tree, I don't really care about the rest of this. I don't have to compute all of it, but I can if I want to. It still runs in linear time. But if I get to here, I don't have to do any more searching for T. And then I can just simply have a little loop that all I have to do is just simply say, okay, well, what's the parent of 3? Well, sorry, the parent of 5 is 3. I can work my way backwards through the graph by following the parents. And then when I hit S, I have the entire path I would like to have. So that's one way you can get a hold of this. There's a lot of neat properties that the queue may have when we talk about BFS. So many that I probably couldn't tell you just today. But I encourage you to explore and think about things that you can do with BFS, because there's a lot of properties it has. This is one of the, probably I would consider this one of the most important things you should know about BFS, is that if you want to find the shortest ST path, meaning the path with the least number of edges from S to T, use BFS. DFS does not guarantee this. So I have a little bit more of an explanation in the notes about this if you're curious. But I just want to give a little summary before I shift gears. Just because we talked about DFS and BFS, I just want to tell you just things that you'd naturally want to think about when you pick one of these two. So I'm going to give you some application, and I'm going to tell you about DFS and BFS, whether you can use it to do that. So the first application is one I've talked about before, is if I want to compute, so these all really fall into the same camp. They're not very hard to change from one idea to the other. The algorithms are almost the same. So if I want to compute a spanning forest or tree, or compute connected components, so if I want to compute connected components of the graph, ends up I'm kind of going a little into my thing here. I can use DFS to do this. My apologies. And I can use BFS to do this. Both of them are capable of doing this. The next one, pathfinding. So if I want to compute a path, so this is one we talked about last day, is you can do that with both of these. How about detecting a cycle? Now, here's the neat thing about BFS. So these cross edges also do serve the same purpose as the back edges for detecting a cycle. So you can use BFS, you could just use these cross edges as a detection tool for the cycle. Because you know that the opposing endpoint will in fact be marked, which would imply there's a cycle in the graph. Just by the same reasoning I gave I think it was a couple lectures ago. So this would be computing or detecting a cycle. My apologies, it's sort of melting into the board here. Maybe that's with the theme for the Halloween spirit, I guess. So you can do that with both of these. And the shortest path, this is the shortest ST path. So to compute a shortest path in the sense that I've talked about, you cannot use DFS to do this, but you can use BFS to do this. So just be aware of that. There are ways you can augment DFS. You may or may not have seen them, possibly, or you may see them in a future class. There's such thing as called iterative deepening. There is a way to modify DFS by adding a little bit more structure for how the DFS occurs, to cause it and allow it to do things like the shortest path. But DFS on its own, DFS vanilla, does not do that. So are there any questions about this? So now you've seen BFS and DFS. These are two standard algorithms that you can use as a building block to design all sorts of different graph algorithms. So these are kind of like your best friends when you first jump onto a graph theoretic problem and you want to explore the graph. These are kind of your two best friends. I know they're mine. So that's a joke, obviously, but I'm just having a little fun with this. So I want to mention one small thing before we end for today. I want to talk briefly about weighted graphs. And then when we come back, I'm going to start talking about a whole new topic involving graphs. We'll be studying so-called minimum spanning trees. So let me just move on over here. I want to define what a weighted graph is for you, because we're going to be using those for the next few lectures. And then we're going to stop here today. Okay, so I want to consider a weighted graph. Okay, so up to this point we've talked about undirected, directed graphs. We talked about a whole bunch of terminology. You can talk about graphs where they actually have weights or costs on the edges or even the vertices. We're going to look at when the edges have costs on them. So we're going to assign costs or weights to the edges in the graph. So that's what we're going to be looking at. So I just want to define what a weighted graph is for you. And just mention a couple small things. I apologize, I'm cutting it really close at the moment. So a weighted graph, G is equal to the pair VE, where there is a number associated with each edge to an integer w. So I'm going to take each edge formally. This is how I would define it for you, the mapping. So I have a weight for, this is my weight function or cost function. For each one of the edges, I'm going to tell you that it maps to some integer. So it'll be a function that takes in an edge, it spits out a number at you. It's going to spit out an integer. Such that W of E is the weight cost of edge E. So that's the definition of a weighted graph. Just as a small couple bit of remarks, I'll talk more about what we can do to represent weighted graphs next day. But I just want to stress one small detail, is that in a weighted graph, if there is an edge, E is equal to UV. In an adjacency matrix, what you would do is you're just going to set the array position, A UV, to be equal to the weight of E, and set the weight of E to infinity otherwise. So if there's an edge that exists between two endpoints, that means that I'm going to have it where I'm going to assign that position. Instead of it being a 1, I'm going to put in the weight of that edge. So instead of it being a 1, it'll be the weight. If it's a 0, I'm going to put infinity. That's the difference here. Now, if I'm using a more OO-based implementation of this, I would store edge objects, and then what I would have is in there an attribute that stores the weight. It doesn't, none of these are going to change much of the details. An adjacency list, this is where I'm going with the other one. If I give you an adjacency list, I apologize here. So you associate the weight with the opposing endpoint of the edge. So just like I said earlier with the adjacency matrix, you're just going to simply you can have edge objects that store the weight or cost with that object, or you can simply store this along with each one of your nodes in that linked list with the opposing endpoint. So when you pull out that information about the other endpoint, you can also grab the weight. So just for simplicity's sake, we can access, so if you do take these approaches, we can access the weight, my apologies, my writing just seems like it's melting, access the weight in big O of 1 time. So just like before, I'm going to assume I'm able to access this weight in constant time in future lectures. So anyways, with that being said, I apologize for taking a little bit more of your time. When we come back, we're going to look and study minimum spanning trees. Okay, everybody? So I say thank you very much, and have yourself a beautiful day. And make sure to have Happy Boo Day on Sunday. Happy Halloween for anybody that's doing Halloween. I'll see you later.